Hello, I am Erdem from Uvision. In this video we will design 4 flip-flops using Verilog. Lastly we will simulate our design in Modelsim, or maybe all of the flip-flops, maybe one. Alright, first let's start with the JK flip-flop. So, as you already know, the truth table that defines JK flip-flop is as such. When J and K are 0, the state is preserved in the next clock. When J is 1, K is 0, that means set operation, so Q is 1. When J is 0, K is 1, that means the reset operation. And when both of them are 1, that means the toggling the previous state. Fine, here I have a clean Quartus project that has nothing inside actually, and let's create some new Verilog file here, Verilog HDF file, and declare our JKFF module as such. And let's end the scope of the module by writing this end module keyword. How many inputs does it have? A JK flip-flop module. It has, of course, input wire J and input wire K, input wire clock, of course, and I want to do something called reset operation in the module. So for that I write input wire reset. So when reset is asserted synchronously, the module will be cleared at the edge of the clock, and output is of course reg with the Q name. Let's align this also for compact view. And what are we gonna do inside the module is that you know that flip-flops work with the edge of the clock. It doesn't matter if it's positive or negative, but the edge is the important case. For this reason, we're gonna create an always block to execute at the edge of the clock, and I want to do that at the positive edges. So post-edge clock is triggered, the block itself is triggered every positive edge of the clock. What do we do is that reset has higher priority than the other inputs JK. So if reset is asserted, we're gonna assign the output state 1-bit binary 0. Alright? But if the reset is not asserted, what do we do is we're going to evaluate the values of J and K, because the output is dependent on J and K simultaneously. Fine, then we can actually switch to relative cases depending on J and K values. For that, I'm declaring a case block here and ending it with the end case keyword, and we're gonna change our case according to concatenation of J and K. So J and K can be 2-bit binary 00. They can be 2-bit binary 01. They can be 2-bit binary 10, and they can be 2-bit binary 11, right? Alright. And when they are 00, what happens is that Q is just preserved. What happens when J is 0, Q is 1? It is very simple, of course. 0 is assigned the state, right? And when vice versa happens, of course, it is also very easy to guess. 1-bit binary 1, and when both of them are 1, Q must be toggled, right? As such. So what is important in case statements is that you must cover every possible combination of the case sensitivity. So here we have 2 bits, right? And 2 bits can be just in 4 combinations here. And we covered all of that. If there were something leaking here, for example, if we had covered only 0, 0 and 0, 1 case, we must have written here a default case to indicate that this default must happen if the inputs are not 0, 0 or 0, 1. If you don't declare something called default, then the code itself will create latches for your circuit, and that's actually a catastrophe. You don't want that. Alright, our module is done, but what I want to do to improve the code readability is that I'm going to declare some local parameters inside the code, local param, and I'm going to just parameterize these bit values to increase readability. So hold. When do we use hold is that in the case of 2-bit binary 0, 0, right? Because if that is the case, we're actually holding the value. So let's do it like this. Put a comma, press enter, go to next line. When do we set? When do we set? We set when this thing happens, right? So then do that. When do we reset? When do we reset? We reset when input combination is 0, 1. Fine. And when do we toggle? So we toggle when inputs are 1, 1, right? Of course. By this time we're done with this module, and it's actually very readable code for me. I hope that's the same for you. And let's move on to the next module. Next module is SR flip-flop, and SR flip-flop is very similar to the JK flip-flop. So I'm just gonna copy the content of the SR flip-flop here. Sorry, the JK flip-flop into the SR flip-flop, and I'm also gonna copy the module declaration. Just change J to S and K to R. The outputs are the same fashioned, but what should be removed is that toggling, because in SR flip-flop there is no toggling operation, and what I previously said comes here actually. We cannot cover this toggle state in the case, right? Then we must here declare a default case to handle the case when S and R are simultaneously 1. As you know that in SR flip-flop 1, 1 case is not defined. Then we're also gonna specify that it is not defined by writing 1-bit binary X to Q in the case of S and R equal to 1, because hold is executed when 0, 0. Sorry, this must be 0, 0, and here also this must be 0, 0. Sorry, this must be 0, 0. Alright, hold is executed when SNR 0, 0, reset is executed when 0, 1 is equal to SNR, and set is executed when S is 1 and R is 0. But what if they are 1, 1? It is handled in this default block. Fine, we're done with the SR flip-flop. Let's design something called D flip-flop. It's actually a basic register that just directly transfers what is present at the input in the edge of the clock. So we have input D, input clock, input reset, and output register. Actually, break doesn't exactly mean register, but let's call it like that. Output reg q. Fine. As you know, D is directly transferred to the output at the edge of the clock. So a very simple implementation. Sensitivity to the positive edge of the clock. Begin the block, please, by writing begin and end. And of course, reset has higher priority. So doing it like this will give reset the higher priority. And in the case of reset, what are we gonna do? We're gonna assign output as output 1, and in the else case, we're gonna evaluate D to Q. So assign Q whatever D is. This is as simple as this. The last flip-flop, let's move on to that very fastly. T underscore FF. So what does T flip-flop do is that if the input T is 1, the state is to be toggled, but if the input is not 1, the state is to be kept actually. So input y RST and output reg q, right? Fine. Let's implement the functionality. Of course, we are sensitive to positive edge of the clock, as in the most cases. Actually, some modules can be sensitive to both positive and negative. For instance, a processor might be, actually they are, as I know, sensitive to both positive and negative, so that speed increases for your operations. What happens in the positive of the clock? So if there is a reset signal, do what? Of course, equate the output to 0. But what if we don't have a reset signal? We're gonna evaluate the T value. So let's create a case statement with respect to T. What if T is let me scroll down. What if T is 0? What if T is 0? Of course, we're gonna keep the state, right? And then I'm just gonna write this. But in the case of T is 1, what are we gonna do? We're gonna toggle that. So toggling is done like this. Q is equal to the not of the Q. Toggling. Fine. By this time we're done with the flip-flops actually. Let's save the file. I'm gonna give it a name ff_lib and clicking compile afterwards. I actually expect an error here because the reason is that first let me observe the log, because yes, error is expecting a semicolon. I forgot to place a semicolon here. Actually, this was not the error that I expected to see. The error I expect to see is that it's gonna give a top level entity error. J and K is not declared. How? Yeah, because they must be S and R, in fact. S and R. So this is the drawback of the copying and pasting. So this is why you, in the object-oriented codes, this is why you try to functionize the same functionality inside the code. It says that fflib is undefined. Yeah, that was what I expected to see. So our top level module is called ff_lib, but inside the code there's no such a module. So to suppress this problem, I'm gonna write a dummy module called ff_lib with fake inputs and outputs, just to fool the compiler, not to give this error. Input wire is in, just dummy things. Output reg is out, and sorry, I'm gonna assign the output as the input changes immediately, like this. Out is equal to in, right? So this is just a dummy module, so that we can actually collect every flip-flop inside the same file, so that in your future works you can import these modules in a by using a single file actually. Alright, it's okay. So it's successfully compiled. Then let's write a Testbench module for what? For, let's say, JK flip-flop. Let's create a new Verilog file immediately, and the module name is what? JK_FF_TB Testbench, and end the module by this. Note that module has no input or output because it's the Testbench. So first I want to instantiate the JK flip-flop inside the Testbench. So let's create an instance of JK flip-flop, and I want to call that JK_FF_what device under test. And if I replace these, actually I won't replace them. I will do something else. How many inputs does this module have? So 4 inputs and 1 output. Then let's call the inputs as J_in, K_in, big clock, and RST_in, and that's all. And wire to observe the output, wire Q_out. So if I replace those by the input declaration, it's gonna be equal to instantiating by writing a dot and then in the parentheses assigning those wires or regs. So it is just exactly the same thing but in a different method. So alright, we instantiated our device under test. Actually what we need is something called test vector, right? But what will be the width of the test vector? So we will specify inside the test vector J_in, K_in, and RST_in. Then it's a 3-bit thing, and I want to call it test vectors. And how many test vectors do we need? Actually I just choose something random as 11. We don't even need 11 inputs, but let's leave it as it is. And of course we're gonna read the test vectors from the PC files, right? Then initially I'm doing that, and we're gonna read a memory in binary format from, let me come to here, from some directory inside the test vectors. Don't forget putting a $sign before the read memory byte. What's that function? Yeah. Alright. Let's go back to our project file folder, and inside that I'm gonna create a text file called JKFF test vectors. Note that the extension of this is .txt. In the previous videos I showed you that the test vector file extension is .tv, but Quartus can read .txt files either, so that's not a problem. We can also read .txt files without dealing with .tv. I'm just copying and pasting the full directory, and inside that I want to specify my text file, so, and just copy the name and extend it by .txt. Fine. Remember that to iterate through the items of the test vector, we need some iteration variable. And inside the initial block, I'm initiating it to 0. Fine. The thing is, when do we we need to generate the clock, right? So clock is generated by writing something called always block, and clock is 1, clock is 0, let's say first. Clock is firstly 0, then I'm waiting 5 units of time, it's picoseconds for this. I'm waiting 5 picoseconds and then toggling it to 1 bit binary 1, and then I'm waiting 5 picoseconds also. So this creates the clock. And when do we want to apply the inputs? We want to apply them at the positive edge of the clock. So post edge clock always block will do our job. At the positive edge, I'm going to apply the inputs. So let's concatenate the inputs as as j in, k in, and rst underscore in. Oh my god, yeah. Fine. And let's assign the item of test vectors to these. Note that inside the test vector file, I'm gonna write the bits in this order, j, k, and rst. And let's do that. At first, what I want to do is assert only reset. Then at the next clock, I want to just assert 0, 0 to keep its state. Then I want to do set operation. Then I want to do reset operation. Actually, the reset is done like this, sorry. And then I want to do toggling operation. So it's like 5 input combinations. And from here we can change the number of test vectors to 4. Of course, after this assignment, I need to increase the element iterator, right? So let's save this with the same name of the module. Save it. I hope everything is as expected. So let's compile and give it a shot. We can observe the log panel to see if something is wrong or not. Actually, let's save this and close this test vector file. It says everything is okay here, and I'm gonna open the Modelsim. Even though the Quartus compiler does not raise any error, the Modelsim compiler may raise, so just get warned about that. And please compile your Testbench file. Click done, no errors here, and expand your work and double click on the Testbench file. Luckily, no errors, no bugs, and everything is perfectly good. I'm gonna import our signals here, just like this, and click this run button. Alright, I just clicked F to zoom in, and note that we have here some excessive outputs. To prevent that, I'm just gonna drop the simulation time to 60 picoseconds and restart it and just run it again. Alright, this time it's okay. Let's observe what is happening here. So at the first positive edge of the clock, you see this is the first positive edge, the inputs are asserted as j equals 1, k equals 1, and rst equals 1. So did it what we expected? Is it what we written in the test vector file? Yes, 0, 0, 1. And on the next positive edge of the clock, let's see what happened. Note that Q was undefined in this interval, but in the next clock it is equated to 0. Why? Because we asserted the reset signal. Fine. At this clock, what do we have? J and K are 0. That means preserve your state. So on the next clock, we must have Q equal to 0. Let's check. Yes, Q is equal to 0 in this interval, obviously. But at the same time, we set J to 1. And what I expect is that on the next clock, the Q must be 1, right? Then it is 1 as expected. So that's fine. In this clock, what did we do? Actually, we set it J to 0, K to 1. That means resetting operation, right? So that is fine actually. And on the last clock, what did we do? We did J and K equal to 1. And the result is observed on the next edge of the clock, and that is toggling operation. So Q is toggled from 0 to 1 as expected. So this concludes this video actually. We have written some codes about flip-flops and then writing a test bench for JK flip-flop. Hope you found this video helpful. Hope you found this video helpful, and if so, please subscribe and thumbs up, and thanks for watching. Bye.